Good morning, my dear students. Another day with online class and with you. So, I wish you good morning and have a tasty day. So, we start our discussion with isomerism exhibited by coordination compounds or isomerism in coordination compounds. We know what is isomerism, and isomerism is defined as the process or phenomenon by which two or more molecules have same molecular formula but different structural and spatial arrangements. So coordination compounds also exhibit isomerism, and in this class we have to see what are the different types of isomerism exhibited by coordination compounds. And in case of coordination compound exists two types of isomerism. So the isomerism in coordination compounds could be classified into two. They are structural isomerism and stereoisomerism. We know the structural isomerism arises due to difference in the structures of the coordination compounds. That means in case of coordination compounds, in case of structural isomerism, the metal ligand bonding will be different in structural isomers. But in case of stereoisomerism, it arises due to different spatial arrangement of ligands around the central metal atom. That means in case of stereoisomerism, the spatial arrangement is different but the structural formula and molecular formula are same. That means the metal ligand bonding are same. But in structural isomerism, the molecular formula is same but the metal ligand bonding will be different even though they have same molecular formula. Structural isomerism is again classified into four. They are ionization isomerism, hydrate isomerism, linkage isomerism and coordination isomerism. In all these four isomerism, the molecular formula may be the same but the metal ligand bonding will be different. Moving to stereoisomerism, it is classified again into two. They are geometrical isomerism and optical isomerism. So we can say in coordination compounds, isomerism could be of two types. They are structural isomerism and stereoisomerism. Structural isomerism is again classified into four. They are ionization isomerism, hydrate isomerism, linkage isomerism and coordination isomerism. Stereoisomerism is again classified into two. They are geometrical isomerism and optical isomerism. So, in case of structural isomerism, the metal ligand bonding will be different, while in case of stereoisomerism, the metal ligand bonding remains same, but their spatial arrangement is different. Now, we discuss one by one the different structural isomerism. So, I told you in structural isomerism, the metal ligand bonding is different, and structural isomerism is of four types. They are ionization isomerism, hydrate isomerism, linkage isomerism and coordination isomerism. Now we will discuss one by one the different structural isomers. See, moving to first one, that is the ionization isomerism. So in case of ionization isomerism, they give different ions in solutions. That means when I take a particular coordination compound and dissolve in water, it gives different ions in their aqueous solutions. That means their molecular formula may be same, but in solvents they give different ions. Take the example. Now I am taking the example here. Here in this case PtNH3 3 times BrNO2 and PtNH3 3 times NO2Br. Both these coordination compounds contains 1 Pt, 3 NH3, 1 bromine and 1 NO2. Here also 1 Pt, 3 NH3, 1 NO2 and 1 bromine. That means the molecular formula is same. But when I take the first compound and dissolve in water, it will give me NO2 minus ions. That means this resulting solution will give me the positive test for NO2 minus ion. But if I take the second compound and dissolve in water, it gives the positive test for bromide ion. That means these two isomers gives different ions in their ionization stage. That means dissolved in water. And this type of isomerism which give different ions when coordination compound dissolved in water is called ionization isomerism. See here, in the first compound, the metal platinum is bonded with 3 NH3 and 1 bromine. That means the metal ligand bonding is between platinum, ammonium ion and bromine. But in case of this compound, the bond is between platinum, ammonia and NO2 rather than Br minus. So metal ligand bonding is different in these two compounds. See this example, the same example. See, I have a chlorine inside the sphere here, but in this molecule the chlorine is outside the sphere. That means during ionization isomerism, ligand can migrate from coordination sphere to ionization sphere and from ionization sphere to coordination sphere. So in ionization isomerism, there is exchanging of ligands occurs from coordination sphere to ionization sphere and from ionization sphere to coordination sphere. Now moving to the second type of isomerism among structural isomerism exhibited by coordination compound is hydrate isomerism. From the name itself we could make it out something connected with water. Hydrate isomerism occurs when water molecules migrate from coordination sphere to ionization sphere and vice versa. That means hydrate isomerism will give you same type of ions, but migration of water molecules occurs from coordination sphere to ionization sphere. See here, in hydrate isomerism, the number of water molecules inside and outside the coordination sphere are different. That means water molecule migrate from coordination sphere to ionization sphere and vice versa. Take the example here. I have three compounds here. In the first compound, it is having 4 water molecules in their coordination sphere and 2 water molecules in the ionization sphere. Moving to the second compound, I have 5 water molecules inside the coordination sphere and only 1 water molecule outside the coordination sphere. Moving to the third compound, I have 6 water molecules inside the coordination sphere and no water molecule outside the coordination sphere. If I take these 3 compounds and dissolving in water, This compound will give you positive test for chloride ion because there is a chloride ion in the ionization sphere. This compound will also give you positive test for chloride ion because there is two molecules of chloride ion, and this also will give you positive test for chloride ions. That means in these three molecules the molecular formula is same: 1 chromium, 6 water molecules and 3 Cl. But their migration of water molecules occurs from coordination sphere to ionization sphere and from ionization sphere to coordination sphere. See here. See here. I have 4 molecules of water inside this sphere. Here I have 5 molecules of water inside this sphere. And here I have 6 water molecules inside this sphere. And there is chloride ion here also, here also, here also. Take down. Now, the third type of structural isomerism is linkage isomerism. Linkage isomerism is only exhibited by coordination compounds having amphidentate ligand. We know what are amphidentate ligands. Amphidentate ligands are ligands which contains more than one donor atom, but it acts as a monodentate ligand. That means simultaneously two atoms cannot bond. Either one or another will bond to the metal atom. Linkage isomerism could be exhibited only if the coordination compound contains amphidentate ligands. See here. So NO2 and NO minus, SCN and NCN minus. These two are examples for amphidentate ligand. That means here either sulfur or nitrogen will bond. Here either nitrogen or oxygen will bond. So if any coordination compound contains this type of amphidentate ligands, it exhibit linkage isomerism. See here. I have example CONH35ONOCl. See here. And I have another example CONH35NO2Cl. In the first compound, the oxygen is bonded to the cobalt atom. Metal ligand bond is between cobalt and oxygen. But in this particular molecule, the metal cobalt is bonded with nitrogen. So it is called nitroisomer, while if it is bonded by oxygen, it is called nitritoisomer. So here NO2 minus is an amphidentate ligand. So from the name itself we could make it out. Linkage isomerism means it should contain amphidentate ligands like SCN minus or NO2 minus. Take down. Now we have to see the last type of structural isomerism, that is coordination isomerism. Coordination isomerism is exhibited by coordination compounds having two coordination spheres. Any coordination compound, if it contains two coordination spheres, ligands could migrate from one coordination sphere to another coordination sphere, giving rise to coordination isomerism. See here, I have an example here, that is CONH3 6 times, CrC2O4 3 times. So here CONH3 6 times 3 plus is neutralized by CrC2O4 3 minus. That means this is a single compound having two coordination sphere. Here we have 1 cobalt, 1 chromium, 6 NH3 and 3 C2O4 ions. Similarly, I have another isomer, that is CO C2O4 3 times, Cr NH3 6 times. So here also we have 1 cobalt, 1 chromium, 6 NH3 and 3 C2O4. This is together constitute a coordination compound, and this together constitute a coordination compound. Don't think these are 4 coordination compounds. This together is one coordination compound and this together is another coordination compound. Now ligands could migrate from one coordination sphere to another coordination sphere. That means from cobalt, NH3 could migrate to chromium. Similarly, C2O4 could migrate from chromium to cobalt. That means ligand is exchanging from one coordination sphere to another coordination sphere. So, coordination isomerism is exhibited by compounds having two coordination spheres. We have discussed the different structural isomerism exhibited by coordination compounds. There is one more type of structural isomerism, that is called coordination position isomerism. This coordination position isomerism is exhibited by coordination compounds having bridging ligands. That means certain ligands bridges two coordination spheres. Such a type of compounds show coordination position isomerism. But in your syllabus it is not mentioned, so I am not taking it. Now moving to the second part, that is stereoisomerism. As I pointed out earlier, stereoisomers are isomers having same molecular formula but different spatial arrangement. That means stereoisomers have same molecular formula and same structural formula. The metal ligand bonding will be same in the case of stereoisomers, but the ligands placed in three-dimensional space will be different. And stereoisomerism is classified into two. They are geometrical isomerism and optical isomerism. Geometrical isomerism and optical isomerism. Now we have to see about stereoisomerism. Geometrical isomerism is only exhibited by square planar complexes and octahedral complexes. That means tetrahedral complexes never exhibit geometrical isomerism. So, in coordination compounds, only square planar complex and octahedral complex exhibit geometrical isomerism. While in the case of optical isomerism, square planar complex never show optical isomerism, but tetrahedral and octahedral complex shows geometrical isomerism. Sorry, optical isomerism. So, geometrical isomerism is not exhibited by tetrahedral complex, while optical isomerism is not exhibited by square planar complexes. Take down. Now we have to see the geometrical isomerism in detail. So first we take the geometrical isomerism in square planar complexes. Geometrical isomerism could be of two types. They are cis isomer and trans isomer. If the same ligands are on the same side, it is called cis isomer. If the same ligands are on the opposite side, it is called trans isomer. So we take one by one and see. See here, first type of square planar complex, Ma2B2. A is a ligand, B is a ligand. So we have four ligands. So this is the structure. Metal, A same side, B also same side. So this is isomer. Now I can place these ligands in the opposite direction. AABB. This is a trans isomer. See here, in these two isomers, the metal ligand bonding is same. The metal is bonded to 2B and 2A. That means these two are not structural isomers, but their spatial arrangement, placing of ligands around the central metal atom is different. So, in case of Ma2B2, it can exhibit cis and trans isomer. Take down. See here. This is the central metal. See, two NH3 molecules are on the same side. See here, Cl2 molecules could be on the different side. Now see here, NH3 in the opposite side and Cl on the opposite side. So this is an example for square planar complex of the type Ma2B2 exhibiting cis and trans isomers. Now take the second case, that is MABCD molecule. MABCD molecule. In MACD, these three geometrical isomerism are possible. See here, these four ligands are different. So I place bromine here as constant and I am changing three other ligands. See here, bromine is constant, changing other ligands. Bromine is constant, changing other ligands. That means compared to bromine, the relative positions of other ligands are changing. So MABCD, that means four different ligands exhibit three geometrical isomers. How? By placing one ligand in a constant position and others ligand are moving in relative to that particular ligand. So MABCD show three types of geometrical isomers. Now move to Ma2B2. See, this is a chelating ligand, or we can say bidentate ligand. See here, metal AB. AB is a bidentate ligand. It is a chelating ligand. So it could chelate in such a way that the same atoms could be on the same side. So we say it is a cis isomer. We could have another arrangement. That means the same atoms are on the opposite side. Here also AB is a chelating ligand. So B is in the opposite side. So this is a trans isomer. So MAB2, that means metal bonded to chelating ligands, shows two types of isomerism, cis and trans isomerism. Now see here, third type, MACB2. MACB2. That means two ligands are same but two ligands are different. In such case of square planar complex, we can have cis isomer and trans isomer. See here, the chlorine atoms are on the same side. So it is a cis isomer. Now the chlorine atoms are on the opposite side. It is a trans isomer. So MACB2 exhibit two types of isomerism, cis isomer and trans isomer. So we have seen geometrical isomerism exhibited by square planar complexes.